Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Fifi Faisha binti Aswali, and I'll start the presentation for this task for the warehouse scale computer. For this task, the slide consists of introduction, storage, cooling and power, server, networking, and monitoring and repair. For this objective of this task is to tell a story about the warehouse scale computer and exposing students to develop in-depth knowledge of the advanced computer architecture. So I'll just go straight to the introduction. I'll just do a brief introduction on warehouse scale computer. I have 3 points here, which are the first one is provide internet services, where as a high bandwidth internet connectivity become much more worldwide in this digital world, an increasing number of applications are being offered as internet services that run on a remote data center facilities instead on a user's personal computer. For the second point is HPC is designed with a million processor that costs $100 million, where this HPC has a much more faster processor and networks between the nodes rather than WSC, because HPC applications are much more interdependent and communicate much more frequently. The third point is a data center, where data center unite different machine and software into one location. Data center and WSC is quite similar but different in very small details. So data center emphasize visual machine and hardware in order to serve various kind of customers. So WSC currently power the services offered by the companies such as Google, Amazon, Facebook, Yahoo, and also Microsoft Online Services division. So they differ significantly from a traditional data center, where they belong to a single organization, use relatively homogeneous hardware and system software platform, and share a common system management layer. So for this is a storage hierarchy of WSC, where from this figure, it attempts to quantify the latency, bandwidth, and capacity characteristic of WSC. For this illustration, we assume that we have a system with a 2,400 servers, where each with a 16 gigabyte of dynamic RAM and 2 terabyte of disk drive. So the key challenge here is for the architects of WSC is to smooth out this inconsistency in a cost-efficient manner. So I'm going to talk about this NAS devices and GPS-like system, where NAS stands for Network Attached Storage, where NAS devices directly connected to the cluster level switching fabric, where NAS tends to be a much more simpler solution to deploy initially, because it allows some of the data management responsibility and keeping the storage separately from computing nodes, which is making the process much more easier to enforce quality of services guarantees. To be compared with the GFS later, so NAS tends to provide high availability through the replication or error correction capability within each appliances, where GFS stands for Google File System, implement replication across different machines and consequently will use much more networking bandwidth to complete write operation. However, GFS-like systems are able to keep data available even after the loss of the entire server and allow high aggregate read bandwidth, because the same data can be solved from multiple replicas. So storage divided into two parts, which are the structured storage and unstructured storage. For this part, for the structured storage, I'll be talking about the Google Bigtable. So on the screen right now, I'm providing this example of Bigtable, which the left side is much more formal, and the right side is much more user-friendly kind of figures, where the second on the right side of figure much more easy to understand by outsiders and users. This Google Big Data actually for this Google Big Data has a burden of resolving temporarily inconsistency to the application using this system. So developers within the Google have found it is inconvenient to deal with a weak consistency model and limitation of the simple data in a big table. So with this problem, with the weaknesses of the big table, they came out with second generation approaches, which are the Megastore and Spanner. This Megastore and Spanner provide a richer schemas and SQL-like functionality while providing simpler and stronger consistency model, which is what the developer need to overcome the weaknesses of Bigtable. So Megastore sacrificed the right throughput in order to provide synchronous replication, while Spanner uses a new time-based API to efficiently serialize globally distributed transaction, which to provide a simpler consistency model to application to wide area replication for fault tolerancy. So this both Megastore and Spanner sacrifice some efficiency in order to provide a much more simple programming interface. For the unstructured data, I'll be using the GFS. As mentioned previously, GFS stands for Google File System, where is an example of storage system with a simple file-like abstraction. So GFS was designed to support a web search indexing system, where the user of GFS typically manipulate large quantity of data, where therefore GFS is much more applicable and further optimized for large operation or anything that works with a huge amount of data. Next, we're going to go straight to the cooling and power. So cooling, we have divided to three features here: open loop, closed loop, and three loop system. So in general, data center cooling system remove the heat generated by all equipment. To remove the heat, a cooling system must employ some hierarchy of loop system. So as mentioned, I have open, closed, and three loop system. So for the open loop system, replace the outgoing warm from the bottom part until to the upper part of this racks. So replaces the outgoing warm medium with a cool supply from the outside, so that each cycle through the loop uses a new material. So for the closed loop system, the closed loop system recirculate the same medium again and again, and transferring the heat to the upper loop in the heat exchanger. As you can see, these blue and red arrows, so it recirculate within the racks, and the function is to remove the heat from the server and transport it to the heat exchanger. Next, I'll go to the three loop system. This three loop system, the computer room air conditioning, you can look at this, you can focus on these blue arrows here. Receive a chilled water or a processed chilled water supply from an intermediate circuit containing a chiller. So the chiller exchanges the heat into a condenser water loop that is open to the atmosphere through the cooling towers. So the condenser water loop get its name because it rejects the heat coming from the condenser side of the chiller. So these three approaches present trade-off in complexity, efficiency, and also cost. So for the power, there's three factors that is important in WSC to measure the efficiency. First is the facility efficiency, server power conversion efficiency, and also server's architectural efficiency. Shown in the screen right now is the equation to calculate the efficiency and the PUE. PUE stands for the power usage effectiveness. Alright. Okay, so it says that the PUE must be greater than 1. So the bigger the PUE, the less efficient the WSC. So this is what the study has found in the paper, which I will put in the reference in the report. Next, I'll go to the server. Server is a cluster low-end server that are preferred building blocks for the WSC these days. So low-end server platforms share many key component in with the very high volume personal computing market. So this will benefit more the from the economies of scale. So however, the use of a very low performing cost can turns out to be unattractive for WSC. So all these small servers may lead to lower utilization. So for this first figure, this is a education time for the parallel task for the SMP nodes increases for three levels of communication intensity. So the execution time is normalized to a single node case and plotted in a logarithmic scale. To be compared with this, figure 2 is a performance of advantage of cluster built with a large SMP server. Note this one is 128. This is 128 core SMP of a cluster with the same number of processor with the low-end server nodes with 4 core SMP for cluster of a varying the size. Next, I'll go to the networking. So servers must be connected, and as for the performance of a service increases over time, the demand of inter-server bandwidth naturally increases as well. So to avoid paying $1,000 of money and more in networking cost per machine, WSC implementers often reduce cost of oversubscribing the network at the top right of the switch. So this is another way to tackle the network scalability, is to offload some traffic to a special purpose network. So these are the concern for the networking. As you can see here, they're using the rules of thumb with 10-10, and so this part is going. This is part the networking in the WSC. Last but not least is the monitoring and repair in WSC. So an efficient fault tolerance software layers must be based on the expectation regarding the set of expectations, which are the fault resources, statistical characteristic, and the corresponding recovery behavior. So the hardware and the software fault can affect internet services in varying degrees, resulting in different service level failure modes. So these are the categories: the corrupted, unreachable, degraded, and masked. So for the acceptable level of robustness, it will differ across those categories. We expect more faults to be masked by a well-designed fault tolerance infrastructure, so that they are effectively invisible outside of the service providers. Okay, so in WSC, it is useful to understand the faults in terms of their likelihood of affecting health of the whole system, such as causing outages and other serious service level disruption. So here, this is also part of the studies. So okay, as you can see here, they conclude that operator cost of misconfiguration errors are largest contribution to service level failures, with hardware related faults, server and networking, where it contributes to 10 to 25% of total failure event. As you can see on the graph here, this bar graph, these are the study they have found, which consists of 500 server. While to monitor the problem and how to repair the services in the event. So while using this Google Health system, so as you can see here, this is to sorry. Okay, so this Google Health system is a time series in a scalable repository to suggest appropriate solutions. So the set of things that Google Health system to monitor its configuration, activity, environmental, and also error data. Okay, so the example of monitoring system that take advantages of this massive data is the Google Health system, as mentioned. So this Google Health system is to constantly monitor every server. So system helps store this information as a time series in a scalable repository where it can be used for various kind of analysis, including the automated machine failure. This kind of approaches so that the machine learning methods able to suggest most appropriate repairs in action. So thank you so much.